So I'm really pleased to introduce Karoline Messenzehl, who's from the University of Bonn. I'm not going to try and say that properly as you should in German. And we're delighted that Karoline's been a visiting student with us for a year and a half, working in the lab, doing some experiments as part of her PhD project at the University of Bonn. And she's really a proper geomorphologist. So she gets out into tough environments, does field work in the Alps, including collecting rock samples with helicopter, which I'm deeply envious of. And this is a very important seminar for Karoline because she's got her PhD viva coming up very shortly. So this is a nice, relaxed, dry run for it. All right, so we're going to give her lots of confidence and so that she can deal with the real examiners very effectively in a few weeks' time. So, Karoline, please.
Yeah, thank you, Heather. As Heather already mentioned, I'm a PhD student from the University of Bonn, and I came here in March 2016 as visiting PhD student, or what I learned as visiting DPhil student, here to Oxford to Heather's working group. And this afternoon I would like to give you an insight into the topic of rock slope instability in alpine systems. And specifically, I would like to show you why studying rock slope instabilities means dealing with a question of scale. And for that, I would say, let's leave Oxford. Should we? Ah, perfect. Let's leave Oxford at least for the next 45 minutes, and let's go to the Swiss Alps, to one of my study sites, the Todtmann Valley. Hi. The Todtmann Valley is a side valley of the Rhone Valley here, and a neighboring valley of the Matter Valley. And I'm pretty sure that some of you may know the Matter Valley and the Matterhorn here, which is the chocolate mountain of the Toblerone chocolate. The Todtmann Valley is a typical glacier trough valley with 14 hanging valleys on either side of its trough shoulder. And we have two main glacier systems, the Bruneck Glacier and the Todtmann Glacier. And to be honest, it's quite shocking to see the glacier retreat during the last years, because when I did my first fieldwork for my PhD in 2013, the glacier was ending here. And when my supervisor came for the first time into this valley in 1977, the glacier was ending here. So we have a glacier retreat of 180 meters. And when I did my last fieldwork for my PhD in 2016, the glacier was retreating behind this bedrock outcrop here, and it was remarkably thinning. So we have within my PhD time a glacier retreat of 180 meters, and in total during the last 30 years a glacier retreat of more or less 370 meters. In my PhD I was mainly focusing on the hanging valleys of the Todtmann Valley, and specifically on these three hanging valleys here. I was working in the Pippi Valley with very impressive limestone rock walls, in the Prenti Valley with highly weathered metamorphic paragneiss rock walls, and in one of my favorite valleys, the Hungerli Valley. And here you can see remnants of the Rothorn hanging glacier. So some of you may ask now, why studying rock slope instability? Why is it important? Why does it matter? So from a geomorphic and natural hazard perspective, it is important because unstable rock slopes are highly prone for rock falls. And these rock falls are a key driver for bedrock erosion and relief evolution. And they are the prime source for sediments which are available further downslope. And after some time, rock slope lead to massive sediment bodies along the foot slopes. And these tailor slopes are very important sediment storage in alpine systems. In the Todtmann Valley, we have more than 220 tailor slopes. One of my colleagues from Salzburg University, he did this very detailed and, to be honest, quite crazy sediment storage landform maps in all 14 hanging valleys. And he found that rockfall deposits cover more than or up to 26% of the total surface area of the hanging valleys, which is a sediment volume of more or less 125 million of cubic meters, which is currently stored within the upper basins. And this really emphasized the importance of rock slope instability for sediment flux and sediment storage. So most tailor slopes in the Todtmann Valley are decoupled. They lead therefore to a gradual infilling of the upper basins. some tailor slopes can be coupled with a lake here, and therefore rock material or rockfall material lead to a lake sedimentation. And tailor slopes are really important sediment sources for secondary hill slope processes. Here, for example, we have a massive rock glacier which is transporting all this rockfall material further downslope to the river. And the global awareness for rock slope instability certainly increased in context of global warming. In the European Alps, we have, since the late 19th century, an temperature increase of 2 degrees. And this is often coupled with exceptional heat waves, like in 2003 and quite recently in 2015 and 17. And during the last decades, the number of rockfalls and rock slope instability significantly increased, both catastrophic rockfalls and small-sized rockfalls. So, for example, here for the French Alps, for the Mont Blanc Massif, you can see that the number of rockfalls per decade constantly increased since 1940, and this is likely linked to the parallel increase of the mean annual air temperatures. So you see, as soon as infrastructure and humans are affected, rock slope instability represents one of the most dangerous natural hazards in alpine systems. And therefore, it's even more important to ask, why do rock slopes become unstable? When do rock slopes become unstable and how often? Although these questions seem easy to answer, they aren't easy to answer at all, because in geomorphology and in earth science in general, there's currently a hot debate about the key controls. Some argue that rock slope instability is driven by topoclimatic parameters. You need a steep slope, a bit of frozen bedrock, a bit of warming and sun, and then here you are, you have your rockfall. But we shouldn't forget that alpine rock slopes were formerly glaciated and are still glaciated, like here, for example. So most alpine rock slopes are still adjusting and responding to their former glaciation and subsequent deglaciation. And this paraglacial adjustment is linked to a glacially oversteepening and warming and thawing of permafrost inside bedrock. So the classical paraglacial concept in geomorphology assumes that immediately after the last glacial maximum 80,000 years ago, or in general after glacial retreat, we have a high rockfall peak. But then with increasing time since deglaciation, we have an exponential decline of rockfall activity until a strength equilibrium is reached. So this is the classical model, the classical exhaustion model after Ballantyne, after Cruden and Hu. But the problem with this classical model is that it's barely tested for bedrock instabilities. It mainly derives from fluvial systems, from sediment fluxes after glacial retreat, which were recorded in rivers. So this classical concept doesn't really consider that we have a discontinuous rock mass, a rock mass which is intersected by joints, open joints, widely spaced joints, densely spaced joints, and we have a rock mass strength. So sure, we can have an exhaustion model, but maybe because of the rock mechanical predefining, rock slopes react to their former glaciation more in form of a rapid response, or likely they react in form of a steady state decline model, or maybe the rockfall frequency is constantly high after glacial retreat in form of a steady state model. So you see, I can't really give you a simple answer to the questions of why, when and how often. And certainly all these factors don't contradict to each other at all, but what is really missing so far is a scale approach. Because how can we evaluate these small scale rock mechanical properties against higher scale, valley scale topoclimatic controls? So one of my hypotheses in my PhD was that rock slope instability is a question of scale, and specifically that the relative importance of destabilizing factors is space and time dependent. Because due to the complexity and non-linearity of geomorphic systems and in general of natural systems, we have to assume that with increasing time and increasing space, at each scale, new system properties and causalities might emerge, sometimes unknown properties. And this has major methodological consequences for causation, because we can't really use our small scale findings to explain something which is going on a higher scale. And in turn, we can't use our valley scale parameters, which we extracted by regional scale modeling, to explain something or to explain the behavior of a rock mass. So without scale approach, we can't simply upscale and we can't simply downscale, which is normally done in geomorphology. But what we need instead is a multiscale approach, an approach which is first specifically looking on each scale separately and is providing for each scale a known cause-effect reasoning and causation. And then the best would be in the end to link the scale, because as Sakna already pointed out, linking the scale is a nut that must be cracked, and that's maybe our task as geomorphologists, as earth scientists, to crack this nut. So, how to crack this nut? In my PhD, I was focusing on these three scales: on the bedrock scale, on the rock wall scale, on the valley scale. And at the valley scale, I applied different GIS-based modeling approaches to focus on all 14 hanging valleys of the Turtman Valley. At the rock wall scale, I was investigating individual rock walls and their tailor slope bodies in several field surveys. And at the bedrock scale, I did a long-term rock temperature monitoring over 2 years, and I was using these data for frost cracking modeling to identify the frost cracking intensity. And finally, here in Oxford, we run several laboratory weathering experiments just to focus on the bedrock scale rock weathering efficiency. So in my PhD, I started with the valley scale, and in cooperation with colleagues from Marburg University in Germany, we applied a random forest algorithm, which is a type of machine learning. And the idea was to quantify and to predict the rockfall activity here in our 14 hanging valleys based on 10 potential predictor variables. So we tested, for example, the time since deglaciation as periglacial forcing. We tested several topoclimatic parameters like slope inclination, slope aspect, elevation. We also implemented thermal parameters like bedrock, permafrost, solar radiation. And finally, we also considered rock mechanical properties like the type of lithology and the joint orientation. And we used the random forest algorithm because it's perfect to evaluate the relative importance of these controls based on randomly modeled decision trees. So to keep it simple, the higher the mean decrease in Gini index, the more important is the parameter for the model to predict rockfall activity in our 14 hanging valleys here. And here you can see our modeling outcomes. And to be honest, we were quite surprised to see that rock mechanical properties aren't really important on a valley scale to explain our valley scale rock slope instability. And the same accounts for topoclimatic parameters to some extent, because sure, we have a northern dominance of rockfall events at northern aspects here, or at slopes which are steeper than 40 degrees. But apparently, according to our model, topoclimatic parameters aren't really the key controls. But what is really interesting to see is that the time since deglaciation is the second most important parameter on a valley scale, which explains the valley scale rockfall pattern. And here you can see that most or half of the rockfall events is initiating at rock walls which are currently deglaciated in the last 10 and 100 years, whereas rock slopes which became ice-free immediately after the last glacial maximum 80,000 years ago, they are more or less inactive. So we have nearly this exhaustion-like model as assumed by Ballantyne. And we were asking now, what is the key driver behind it? Because sure, we have this periglacial reaction, but what is really the driver? And our model shows that it's the permafrost probability, and specifically the warming and thawing of permafrost after glacier retreat, which is the key driver for our regional scale rockfall pattern. So you have to imagine that immediately after the last glacial maximum, the bedrock was totally frozen. But with increasing warming and thawing of permafrost, the shear strength of the bedrock decreases and the bedrock becomes more unstable. And today you can see that most of our rockfall source areas lie within boundary permafrost conditions, and these boundary zones are highly sensitive to respond to external forcing, external climate forcing, like exceptional heat waves in 2003. So in a later stage in my PhD, I was wondering, do we have the same parameters and especially the same relative importance of controls at a rock wall scale? And therefore we did a principal component analysis with basically the same input parameters which we used at a valley scale. But this time the parameters derive from individual rock walls here in our 3 hanging valleys. For example, to test the influence of the mean annual rock temperature or of the frost cracking, we installed several rock temperature eye buttons at these 12 rock walls here. We used eye buttons in 10 centimeters depth, and for data management we used a mobile phone app, which is really clever in very steep terrain where you have to hold yourself and at the same time you have to make sure that you don't lose any equipment. And I'm really good in losing equipment, therefore I really can recommend this app. And a typical rock temperature record for northern rock slopes, for very active rock slopes, look like this. We have mean annual rock temperatures here between 2 and 0 degrees, which indicates at least boundary permafrost conditions. We also have a high number of thermal cycles during summer, up to 28 degrees, which is quite high for northern aspects, especially at an elevation of 2,800 meters. And we have some daily frost cycles here in autumn, but what is most important now, we have this long period of up to 2 or 3 months of constantly frozen bedrock. And imagine we have water or moisture saturated bedrock and bedrock temperatures below 0 degrees and minus 10 degrees. Then we have the perfect condition for the slow formation of segregation ice within pores or crack tips. And this slowly growing ice within bedrock pores can develop pressures and high stresses, and these pressures are efficient enough to crack the bedrock. And we were wondering what intensities of cracking, of frost cracking, are to expect. And therefore we estimated for all these rock walls here the frost cracking intensities using the model of hails and Röhring. And it was really interesting to see that the highest frost cracking intensities here are mostly at the near surface, within 50 centimeters bedrock depth. So this is the zone which is highly intersected by joints, which is highly weathered. And therefore, if ice segregation is really efficient here in this zone, then we have to expect near surface shallow detachment of rock falls of smaller sizes. But you also see we have ice segregation within very deep bedrock depth of 400 centimeters, especially here in this valley where we have likely frozen limestone rock walls. And if ice segregation here is efficient to activate shear plains, deep-lying shear plains, then we have to expect large or high magnitude rock slope failures. To get a better idea about the potential rockfall sizes and magnitudes, we also did geotechnical scanline surveys along all these rock walls here. I always had a very clever student with me who helped me to detect and to map and to estimate all joint properties like joint opening, joint spacing, joint orientation, joint length. We also quantified the rock mass strength by using the Schmidt hammer, for example. And as I said, I'm really good in losing equipment. He was really good in finding the Schmidt hammer, especially within snow and ice and big boulders. So yeah. Okay. So that's not showing the. Okay. Normally you should see here a rock wall. So we identified for all transects the rock mass strength, which gives us an idea about the instability or stability of the rock. So the lower the number, the more unstable is the rock. And we also identified the main joint sets, which you can't see now, which is here you can see it, surprisingly. No, I can see them. Anyway, And we also identified the main. Oh, it's not working. The main kinematic failure mechanism, because when joints intersect each other, we have to expect wedge failures. Where joints dip into the slope, we have to expect small-sized topple failures. And where joints are widely spaced and dip out of the slope, the probability of large planar slides is quite high. So you see, or you can't see it now, but on a very small spatial scale, we can have a high variability of rock mechanical properties. And this is really important. And we also did sedimentological tailor slope analysis along all these transects here, just to get an idea about past rockfall events. Because we mapped the block size and the block volume along all these transects to get an idea about the volume of rockfalls which were already deposited. So finally, we used all these parameters here for our principal component analysis, and what we could see is finally that more than 50% of our spatial rockfall variability is mainly driven by the morphometric and thermal rockfall regime. So permafrost degradation, frost cracking, steep slopes, long slope profiles are the key driver on a rockfall scale for our rockfall scale rockfall pattern. But what is now really interesting that we have additional 21%, which can be explained by the rock mechanical preconditioning, in contrast to our regional scale modeling, because there apparently rock mechanical properties weren't really important. But now on a local rockfall scale, the rock mass strength and the joint orientation are to some extent key order, first order controls. And specifically the joint orientation in relation to the slope aspect is really important, because we could see that most rockfall events initiate at rock walls with in-dipping joints. And this is quite surprising, because normally in-dipping means a higher stability. And in turn you can see that a lower amount of rockfall events is taking place on rock walls without dipping joints. And this is also surprising, because out-dipping slope parallel joints means actually a very fast activation of shear planes and a very fast erosion. But this north-south contrast between in and out-dipping joints mainly results from our Alpine tectonic folding. So our present-day joint orientation of our metamorphic rocks are parallel to our regional scale tectonic folding within our study sites. So our present day joint orientation is parallel to the tectonic bedding. And this is to some extent a path dependence, which means that past regional processes are still predefining our present day local rockfall activity. So to come back to this paraglacial model which I showed at the beginning, our valley scale modeling it confirms quite well the exhaustion model after Ballantine, with a very high rockfall peak immediately after declassiation, followed by a subsequent decline. But when it comes to account for smaller scale, rock wall scale, rock mechanical properties, we have a more complex rockfall pattern. Because at rock walls with a very low rock mass strength and outdipping joints, we have a very fast paraglacial response. But as soon as all material is eroded here, nothing is going on anymore, or at least it's only a very low rockfall activity. And at rock slopes, where we have a very high rock mass strength and in-dipping joints, the stability after glacial retreat is first quite enhanced, and the paraglacial response is delayed and weak, but then we have a high rockfall activity until today. So to come back to our principal component analysis, the ordination diagram between the first principal component and the second principal component shows another very interesting outcome, because apparently different rock walls are controlled by different parameters. So, for example, rock slope instability immediately after declassiation is mainly driven by permafrost thaw, permafrost warming, over-steepened slopes, and frost cracking. And rock slope instability during a late paraglacial state at rock walls which are ice-free since 100 or 1,000 years, they are mainly driven by their rock mass strength and rock mechanical properties. And rock slopes, which are already adjusted to a non-glacial condition, which became ice-free immediately after the last glacial maximum, where we have actually today a very low rockfall activity. They are mainly driven by topoclimatic parameters, by a high solar radiation, high mean annual rock temperature, and a high variability. And the exposition of the slope becomes the limiting factor. So you see, with increasing time since deglaciation, although the relative importance of destabilizing factors change. So we have a time-dependent influence of rock wall destabilizing factors. And this is most important for the frost cracking intensity, because our data show that the frost cracking intensity is highest immediately after deglaciation, and not only highest, but also we have the deepest frost cracking intensities, and therefore it's very likely after a short time delay to have high magnitude rock slope failures after glacial retreat. But then with increasing time since deglaciation, the frost cracking intensity decreases, and also the depth, which means we have more small-sized rockfall failures after a long time after deglaciation. So to come back to this model, it shows that the first rockfall peak here is mainly driven by permafrost thaw, permafrost warming, and oversteepening of slopes. And then the lower rockfall activity here in a second paraglacial period is mainly driven by topoclimatic parameters like slope variability, high solar radiation, and the exposition. And this has immediately an influence on the frost weathering efficiency, because we have first a very high frost weathering efficiency, which is subsequently declining. So I said the Hungerli Valley was definitely one of my favorite valleys, and I spent a lot of time there. And after some time I was wondering that the rockfall deposits of neighboring rock walls can look completely different. So here, for example, we have a very homogeneous small-sized rockfall depositional pattern, and here we have massive boulders. And even though that the rock wall source areas are neighboring rock walls of 100-meter distance, and they have the same characteristics like the same aspect, the same solar radiation, the same inclination, the slope length, which is really important for the fragmentation of the rocks. And we have also a same or similar permafrost probability, and both rock walls are within a same paraglacial window. So you can see that neighboring rock walls with actually the same topoclimatic and cryospheric input parameter or characteristics can have completely different rockfall magnitudes and likely frequencies. So we quantified the rockfall frequencies for these two rock walls here. The white is one rock wall and the black is the other rock wall. And you can see here the frequencies of frequency of rockfalls per year, and in turn the rockfall return periods. And if we only focus on the mid-slope, you can see that one rock slope is supplying 10 rockfall events per year, and one neighboring rock wall, which is only 100 meters in distance, has rockfall return periods of 100 to 1,000 years. So I don't want to go too much into detail into this figure, but the key point which I want to make is that two neighboring rock walls can have completely different rockfall frequency magnitude patterns, even though their topoclimatic and cryospheric parameters are the same. And that's simply because of the high variability of rock mass strength and joint properties. So if we pick, for example, one paraglacial window here, that means that two individual rock slopes can have a rockfall magnitude frequency pattern which is highly shifting around the mean. So this is really important for post-diction and prediction of rockfalls, because if we want to predict the rockfall activity for one individual rock slope, we can't use our valley scale models, or we can't use our long-term scenarios. We have to become smaller in scale, and we have specifically to focus on the rock mechanical properties. So finally, let's come back to Oxford, to the GeoLab, because in my final stage of my PhD, I was mainly focusing on this last paraglacial phase here, and on this very low rockfall activity and frost weathering efficiency. Because I was wondering if the low frost weathering efficiency here is really the whole truth of the very low rockfall activity here. And this is apparently a bedrock scale question, because there must be something going on a micro scale, on a pore scale, which is explaining the very low rockfall activity. And therefore here in Oxford we run several laboratory experiments, and one of the cliffhangers was actually this kind of rock temperature record. Because sure, we have this window of frozen bedrock during winter where ice segregation is possible, but we also have daily frost cycles during autumn where the ice crystallization within pores is potentially possible. And we also have a high number of thermal cycles up to 20 degrees of a very high frequency during summer. So we were wondering if this autumn period here of daily frost cycles is sufficient enough to damage the rock. If ice crystallization, which is caused on a daily time scale, is efficient enough to cause damage in our metamorphic rocks. And then we were quite interested in the efficiency of thermal cycles during summer, because currently there's a hot debate about the influence of thermal cycling. Kevin Hall, for example, he's a geomorphologist, he says that Alpine geomorphologists often ignore the role of thermal cycling. We are all always focusing on frost, permafrost, frost cracking, but the role of thermal cycling, especially during summer, is really rarely considered. And this is a problem, because current and recent studies show that thermal cycling during summer can trigger rockfalls. And this without any influence of rainfalls, without any influence of frost, earthquakes, simply because of the thermal cycling during summer. And this was mainly shown by Collins and Stock for the Yosemite National Park. And they showed that thermal stress loading within the bedrock on a bedrock scale can trigger rockfalls and can cause slow rock damage. And what is really interesting, they also hypothesized that the thermal cycling during summer can maybe enhance the efficiency of other frost or rock weathering processes. And this was our starting point, because we were thinking, okay, maybe the sum of many summers, of many summer thermal cycles have any influence on the efficiency of daily frost cycles. And therefore we run several laboratory experiments, and for example 80 frost cycles here in the climate cabinet here in the GeoLab. And important is that we use 2 different sample groups of each 15 samples. And one of these sample groups was pre-stressed by 100 thermal cycles. So the idea was to test this influence with only one sample group here. So what kind of material did we use? This is a longer story, because at the end of my PhD, my research became low-budget research, and therefore I had to collect all these stones without any clever student this time. I had to wait for a bit of money to pay the helicopter, at least from my hanging valleys here to the parking place. I had a very nice supervisor who drove all these samples of 80 kilograms with his wife during his holiday from Switzerland to Bonn in Germany. I had very nice students who packed all this material and then sent them to me to Oxford. And here in Oxford, Hong and Mona did their best to cut the rocks. So finally we had enough samples, 30 in total. And another thing was that we wanted to test the preconditioning of the rock mechanical properties. So we splitted our rock sample groups in 2 different sample groups, and we used one half with horizontal cleavage. So they are metamorphic rocks of low porosity, and they have distinct cleavage zones. And some of them had a horizontal cleavage because we wanted to simulate here on a bedrock scale the higher scale outdipping joint conditions. So we wanted to try this gap between bedrock scale and rock wall scale. And the other sample set had vertical cleavages, just to simulate the in-dipping joint conditions. So we did several measurements, and I only want to show you one outcome, which is the relative change in open porosity, because the open porosity is quite a nice index or proxy for understanding how weak the rock becomes and how efficient it is for pathways, for water pathways. And this is really important for frost cycling, for example. So you can see here our both experimental phases. And in the first experimental phase, it's really interesting to see that the rock samples which were exposed to thermal cycles became more porous. So the porosity, the open porosity, increased from about 2 to 22 degrees, which is quite high for low porosity bedrock or for low porosity rock samples, like in our case. And then in the second experiment of 80 frost cycles, we can see that first that all rock samples reacted. So apparently the ice crystallization was efficient to cause in all rock samples at least minor damage in sense of enlargement of pores by the slow crystallization of ice. But what is now really important for us is that rocks which were pre-stressed here, these upper two craft, they reacted more intensively. And apparently the pre-stressing from the from the period here, from this experimental phase A, was efficient to prepare the rock, to make it more sensitive for later ice crystallization. So apparently the accumulation of stresses and the subcritical thermal fatigue can enhance ice crystallization in low porosity metamorphic rocks. So to come back for last time to this model here, we can see that, or it's still true that ice segregation at a near surface can detach shallow rock fall or can induce shallow rock detachment. But in addition, ice segregation at a near surface becomes relatively more important in this final stage here. So we have, in addition to this ice segregation on a rock wall scale, also a bedrock scale bedrock damage. And it's likely that the efficiency of ice crystallization is enhanced by summer thermal cycling. So you see, during the last periglacial period, when we have a low rockfall activity, it's mainly the influence of microscale rock properties like cleavage or porosity which drives our rockfall activity here. So to come to my conclusion and to come back to my three questions of why do rock slopes become unstable, when and how often, I really hope that this concept here will be tested in different study sites and will be tested for different lithologies, because I think it's really helpful to show that the timing and the intensity of rock slope instability after glacial retreat is driven by time and space dependent variables. So if we want to predict, for example, the rockfall activity for individual rock slopes, we have to think about which scale, which factor is most important for us. So for example here, this is really important that the frequency and the rockfall activity of one rock wall can highly shift around the mean. And this means we should focus on the interplay of different time and space dependent controls. So we have large-scale topoclimatic parameters, which in turn control the efficiency of rock weathering processes on a very small scale. And then we have large-scale tectonic geological processes, which in turn control our rock mechanical behavior on a very small scale, on a rock wall scale. And sure, in alpine systems, we should not forget that alpine rock slopes still react to their former glaciation and subsequent deglaciation, often in form of permafrost thaw and warming. So what is next? Here you can see the predicted temperature evolution for the European Alps, and you can see, according to this scenario here, we have to expect for the first half of the 21st century a temperature increase of 0.25 degrees. And for the second half of the 21st century, even an accelerated trend of 0.36 degrees. And at the same time, the population in and around mountain areas is increasing. So to refer to this citation here, with ongoing climate change, alpine rock slope instability will probably become a more serious issue in coming years. And therefore, I think we as geomorphologists or as geographers, as earth scientists, we have great methods to tackle this issue. These methods are constantly improving. We have great data about past rock slope instability, about potential controls, and we will gain many more data. So I think what is really important now is maybe to think about scales, to think across scales, because I think scale thinking can be really important here and really helpful to do proper predictions about rock slope instability, and can help us to make this upscaling and downscaling. For example, in our study site, it was the Alpine folding, which still determines the rock wall scale joint orientation, and still the cleavage orientation on a bedrock scale. So joints can be a really good link to link the scales. Thank you.